Go for it. Thanks.
As we didn't really do introductions yesterday, can I have a show of hands? Who is working experimentally on laboratory systems? One person. Yay! So I know the people in the room that work on neutron stars. That leaves me to assume that the rest work on modeling of laboratory systems. Is that correct? Okay. What do you work on? Cold atoms. Okay, but so you look at like cold atom systems and you model them in the lab systems, right? Okay. I'm briefly going to sort of like talk about some of the aspects that Niels touched on yesterday. So I'm going to start with like giving a bit more detailed overview of the different superfluidity and superconductivity parameters that we have in neutron stars. Then, well, I'm a neutron star astrophysicist, so I'm going to talk about how we can actually observe these in a little bit more detail and why that might be not so straightforward to actually learn something about the star. And then I'm getting onto sort of like the majority of the talk, which will be about how we can actually probe some of the aspects in neutron star physics in the laboratory and what I mean by that. Okay, so when I talk about a neutron star, typically when I model these objects, what I have in mind is sort of like a picture like this. So we don't really exactly know what the different layers in the neutron star are and what the individual or where the individual layers start and stop, because that kind of depends on the equational state of very dense matter, and we don't have information about that that's well known. So we sort of have like this canonical understanding that for an equilibrium neutron star that's something like 10 to the 4 years old, has something like 10 to the 6 to 10 to the 8 Kelvin, and has sort of these distinct layers that have formed as the star has cooled. So for the kind of picture that I usually have in mind, I separate the star into a crust that's composed of an ion lattice, electrons, and neutrons. And I have something like a core that spans the majority of the whole radius. So you see radius delta T is something like 9 kilometers versus a 1 kilometer thick crust. But this obviously carries the majority of the star's mass, because you see that the density can sort of increase from something like 10 to the 11 to something like 10 to the 15 grams per cubic centimeter, okay? So these are densities that are higher than nuclear densities that we know from atomic cores. So this is like really beyond what we can really probe on Earth. So you kind of have to like make extrapolations on how matter behaves and kind of like try and figure out what the equational state looks like. That's why we don't really know where these interfaces exactly are. There's a lot more stuff happening down here that I don't really know a lot about. So it could be an entire like inner core that has a lot of exotic physics, like exotic particles, hyperons. I'm going to ignore this for now, but in principle, a lot of the aspects that I'm going to talk about, you can sort of like extrapolate to the quantum phases that might be present in this layer at very high density. Okay, so within this specific picture, we already know that we have at least 3 distinct superfluid components. So we have a superfluid component at the in the inner crust, which is close to this, what we call the crust-core interface, and then we have superfluid neutrons in this outer core and superconducting protons in this outer core. Okay, and just to like sort of reiterate what we said yesterday, typically when we model this, we assume that is a zero temperature system. So I don't have excitations within the individual components, but I assume that I have distinct superfluid components and no excitations present. So that's what we typically call normal fluid in the lab system, and is not present in this case. Okay. So for the 3 different systems that we have, people have calculated using sort of BCS type calculations or generalizations of that, the pairing gaps that are associated with these distinct superfluid and superconducting components. So there's 4 curves here. So they're sort of typically for the crustal superfluid and the core proton superconductor, which are plotted here as solid light blue and the dashed dark blue line. And they're sort of on the order of 1 MeV. And they typically assume to be achieved by singlet pairing. Okay. Whereas the neutrons in the core of the star that overlap with the proton superconductor here are expected to pair in a 3p2 triplet state. Okay, so because of that, the pairing gaps are much smaller, And you do see two different types of curves plotted here. So because of the fact that you sort of have to account for like higher order interactions, and it's really not that clear how free particle interactions really work at that high densities, it's not quite clear where this gap actually sits. So I just plotted two different triplet gaps. Although I should probably say that the purple one is probably closer to the realistic model that most people use. So if you have equation of state for this system, you can translate those gaps into the critical transition temperatures of the star, and you can plot them as a function of density. So if you go back to that plot here, so we go here at 10 to the 14 and we go to 10 to the 15. So I just plotted these curves within the core essentially. And if you just translate them from this picture to this, you sort of see that if the star is initially very hot, you start somewhere up here, and you, by cooling down, so time progresses, you essentially just like move down this line somehow. And the first thing that you will hit, the first transition temperature, is the superfluid transition in the crust. So that's the first condensate that you will form. In the core, you're probably more likely to hit the superconducting transition first, and then after you've made the superconductor, you will eventually form the superfluid. Okay, so those are sort of like typical gaps that we use. Obviously, we don't really exactly know what their shape looks like, but sort of the order of magnitude and sort of the position is probably correct. So we talked about like dimensions of these systems, sort of like in a bit of an abstract way yesterday. So I just wanted to like give you some of the numbers that we have for these parameters in the actual neutron star. So in the vortices, the neutron vortices in the stellar core, they have a size of something like 10 to the minus 11 centimeters, so something like 100 Fermi. And if you just use the standard expression from BCS theory to calculate the size, what you get is that actually is a function of the density inside the star. So it's a function of the proton fraction, which we denote by xp. It's a function of the total mass density. Every time we have rho 14, that's just in units of 10 to the 14 grams per cubic centimeter. This is the transition temperature in 10 to the 9 Kelvin. And then we have these m over m star parameters, which are just effective masses which are caused by entrainment in the interior. Okay, so this is the vortex size for the 3p2 system, and in the crust, they're typically going to be an order of magnitude smaller. So the singlet vortices are going to be a little bit smaller than the triplet vortices. If you kind of relate that to an average vorticity of the system, you can define how many vortices you need per unit area to sort of match those numbers with actual observational values for the periods of these neutron stars that we have. And typical, I'll show you a few more values in a bit. So a typical rotation period for a neutron star would be something like 10 milliseconds. So if you want the superfluid to rotate at 10 milliseconds, you would need something like 10 to the 5 vortices per unit area. Okay. You can relate that to a typical intervortex spacing.
You mean per centimeter? Unit area is centimeter?
Yes, per centimeter, yeah. Obviously, you would have lots of those next to each other, assuming they're straight.
By vortex size, what do you mean? Core size?
Coherence length, yeah. So they're typically separated by something like 10 to the minus 3 centimeters, which sort of gives you like a reasonable spacing for these structures in the core and the crust.
So the spacing is to be order of the size?
The spacing is of, no. So the size is like, so there's like 8 orders of magnitude difference.
So
this is the size of or the width of the vortex, the core size, and this is their separation. So you have like, you have to wait quite a bit before you hit the next one in units of this.
so these things are very
diluted.
small.
Yeah. Yeah, so it's kind of like important if we come to the next bit. So these, yeah.
And this is assuming that all the vortices are equally spaced.
Yes, that's assuming that's essentially like you have a cylinder and you have a regular vortex area structured in that. If you have like that kind of tangle that Nils talked about yesterday, well, I can't really give you an answer. Yeah.
What happens when vortices in the triplet pairing region migrate into the singlet.
Maybe we can leave that for a later conversation because yeah, so that's one of the things I wanted to talk about later. Okay, so we already talked about mutual friction forces yesterday. There was a little bit of confusion, but I think that resolved itself in the end. So the typical mutual friction force that we write down for the core looks something like this. So this is typically the form that we write down. So we have these parameters B and B prime in there. And I just thought I'm just going to show you for the crust and the core how these parameters typically look like. So most of the time we model this, we assume that they are just constant numbers, but they're far from constant. So in the core, for example, the most common mechanism is that you scatter electrons off the magnetic field of the neutrons vortices. And if you plot this, it's a function of the appearance length, so the gap. So you kind of like need to like have some input parameter what this gap looks like. So you get these like sort of like curved shapes that sort of represent the gap that I showed you earlier. This dashed line is the number that, or the approximation that you typically see in a lot of theory papers. So in principle, there's already some like, well, discrepancy between the numbers that we typically use and how this shape actually looks like. You might say, well, it's only like 2 orders of magnitude, but what it kind of distinguishes is like the timescales which individual things couple. 2 orders of magnitude on an astrophysical timescale might not be so much, but if you actually want to like really understand what's going on, you kind of like have to do a bit better than just saying, well, let's use this blue line. Yeah. So that's for the core. That's just one mechanism. It's kind of the most common one that we use. There might be others. It's definitely a lot less clear how these parameters, how this frictional force would look like if we, for example, have pinning presence and we have other kind of like dissipation mechanisms in the core. But in principle, I think the main takeaway point is already for the core. Well, we typically use this, but there could be other things, and it's definitely density dependent. I had a look at the crust physics sort of in the last year to try and understand how the crust coupling actually affects physics. And I just plotted these crust parameters. So there's 3 different mechanisms here that I sort of like briefly mentioned yesterday when Sanjay asked. So there's, in the crust, you don't have a proton superconductor, so you can't have the vortices scatter of that magnetic field. So the vortices, they are not magnetized. But there's other kinds of like dissipation mechanisms that you can have. So the most common one, or the most common 2, I would say, is you have a vortex and you move that past the lattice nucleus, and they will have some kind of like pinning interaction. And if you move that vortex very fast, what you're going to do is you're probably going to start shaking that vortex. So you're going to excite Kelvin waves along that vortex, and that by putting energy into those Kelvin waves, you're essentially dissipating energy. So you slow down the vortex. There's 2 different papers essentially that have looked at this. They do look at the same physics. They arrive at different expressions because they make different assumptions about the actual interaction ranges for these pinning potentials. So you sort of like see those are like these different curves at the top. So it's really not that clear at all. Well, they're definitely not constant. So this is like 10 to the minus 7 over here, and it's like 0.5, like really close to the maximum here. So we have like a massive range of values from the inner crust to the crust-core interface. So if I would like write down a hydrogen model where I just pick one value, well, which of these would I pick? And that's just for one mechanism. So for the other mechanisms, I can get like even lower. So if you have the vortex move past the lattice nucleus relatively slowly, you won't shake the vortex, but you will start shaking the lattice. So it will excite lattice phonons, and that's much weaker in principle. So that is that blue dashed line here. You also see that goes to something like 10 to the minus 15. So that's really, really, really weak. But again, it's like got this like structure depending on like where you sit within the density.
Why would vortices move? Because typically, if you rotate the superfluid, they form a lattice which rotates with it.
Well, so the star spins down, right?
Sorry?
The star spins down. So I've kind of like observed this object, and I'll show you this in a second. I know that the rotation period increases, so it spins down. So on average, if I use
very slow.
Yes, but I mean, you would still do that. So we're going to talk about glitches, which is kind of like the main mechanism in a bit, and I'll tell you how many of these vortices you actually have to move, and it's quite a lot. So they definitely would have to like, they will move eventually.
How fast do they move?
Good question. I don't think we really have an answer to that yet.
But when you're talking about speeds that have these effects, then
Something
you're thinking
like
about during a motion,
relative
during a
motion.
event.
Yeah. So after like, well, so it's this essentially some kind of like frictional mechanism, right? So I have to like unpin them first, and then something happens. And so the relative velocities are something like, well, you can get estimates between 10 to the 6 centimeters per second up down to like 10 to the 2 centimeters per second.
On nuclear scales, those are very small velocities.
Well, those numbers are calculated with those small velocities. So despite the fact that they are small, they still give you these kind of parameters. So this is actually velocity dependent. So this gives you relatively, I mean, this is really strong coupling for that kind of parameter set.
And so the betas in your model should have a velocity dependence.
Yeah,
in the
so
coefficient
actually,
as
so
well.
the Kelvin ones do, the other ones are velocity independent. Those are not. Did you talk about velocity, like of that system, of those kind of systems, how fast they move? Did you talk about that last week?
Not really, no.
Okay.
Vanessa, just one question, comment kind of thing. From the models you've got there, it's not then clear whether when you go from the core, you take a vortex through from the core to the crust, whether it goes from a strong, relatively strong friction to a weak friction, or the other way around.
Yeah, I'll get back to that again in a second. I'll show you some other setups. Okay.
So what happens at the ends of the vortices? I mean, presumably there's some region where it's superfluid, right? But then it starts at some point and it ends at some point.
I have no idea. I mean, in principle, this would like assume to some extent that the vortices, they actually like extended like linear lines throughout the whole inner crust. I hardly doubt that that's the case. I do assume that there's probably some kind of like length over which I have a straight vortex segment, and then they sort of like start bending, or they even like detach. So I don't really know what happens on those ends at all. I don't think anyone really has ever looked at like those physics.
They can end on impurities, I believe. That's one thing. They can end on the border of the system. So from the way you have a phase transition from one phase to another, we can end up there.
Okay, so for
just one more question. So
yeah, sorry, it was
So
just a bit
what-
slow. Yeah.
so in this equation form, what is Vn and V?
Okay. So Vn. So in the core, I get dissipation because I scatter the electrons of the vortices, and I can write that effective mutual friction force as depending on the relative velocity between the superfluid neutrons and the electrons. So that's just the relative velocity between.
But electrons stay essentially relativistic, right?
Yes.
So you could see there, right? And that's basically the dominant factor there. Vn, it's negligible in comparison to the speed of the electron.
Yes. So yes, you can do that in some.
No, you have to be careful here.
This
This is the fluid velocity. This is not the microscopic
that's true.
velocity with which the electrons
Yeah. So this
might be
is some
moving.
kind of
This is-
average parameter.
If I look at
It could be the sound velocity. No, so you mean you have fluid of electrons, the current.
Yeah. So then,
So
larger
what are
scales,
those
I look at some.
velocities? What's the magnitude? Where they come from?
Omega plus I.
So they,
You see, because if I have, you see a conductor that push current, you see, that's what's the velocity? It's the diffusion.
It's like the driven velocity.
Yeah, but what it's in this
so
space, you see
there, I
where it
guess,
comes
what you kind of assumed is that that's your normal fluid, so you've got electrons and protons
Protons
and everything.
together,
So that, in a way, would be the speed that you get from rigid rotation of your pulsar. And then the neutron superfluid is
Relative.
rotating at a slightly different rate. And so you have a relative flow. But because microscopically, of course, you're right, the electrons are shooting all over the place. But
No,
then when you average
If
over,
they're drifting, you see, they should go through a lattice, you see, and you have simply to calculate by regular friction like we do the model, for example, use like incandescent physics, you see, so that's relatively straightforward to calculate.
you're
But I don't know what impurities you have there, you see, because you're in the core, you don't have any impurities, so I don't know what to make
Well,
of
I
it.
guess you're assuming that it's the magnetic field that's
Yeah.
keeping
So I do
Well,
still have a
to
field
the-
somehow.
Well, it's
Yeah.
So you've got to look on rather long time scales here where this is all happening.
I I really don't understand where it comes from, where it could come from.
The electrons and protons are strongly coupled to each other, right? You don't even need to remove the
The electrons, no, the protons and electrons, I don't think they're coupled strongly. The electrons move with speed of light.
Well, it depends on the
No, no,
scale
no,
that you're
no,
looking at,
No,
right?
on an average, they're coupled strongly. So if you create a clump of protons somewhere, the electrons will
But
come
you
and-
don't have inside the core, you don't have clump.
Yeah, that's what I'm
Exactly.
saying. So you cannot create clumps, big sizes of
So then
charges.
how do they move?
So
You don't have impurities to scatter, so you don't have drift velocity. So I think everything becomes totally unclear.
Another question, I'm sorry, I'm very naive about this. Okay. So, are these like soda straws all standing up parallel, or is it like spaghetti where they're all twisted?
Well, so in the most models, we just assume they're like straight spaghettis, which is definitely not the right thing, but I guess that's like the state that we're currently at when you kind of model it. Sorry?
Uncooked, yeah, soda
Uncooked. Oh,
straws.
sorry, yeah.
Soda straws.
Very, very al
Soda
dente
straws, yeah.
spaghetti.
And why did they assume that?
Well, so the thing is, like in principle,
It's easy to do.
it's easy, but so the star has definitely some kind of magnetic field and it has some kind of rotation. So I guess, were you here yesterday? Yeah, you.
The first topic.
Yeah. So I
If
mean,
you don't have turbulence.
yeah. So if you don't have that, but to some extent, you should still have some on large scale, some kind of like directionality as well of your field and your rotation vector, right? So on some large scale, you should definitely have some kind of like ability to draw some magnetization in a specific direction. And on small scales, you could potentially assume that you recover that in some form or other.
And there's a restoring force which wants to make these vortices kind of like this.
That's not included, but you can like add a tension term here. So you can extend that to a tension, which is not given in this equation. But so this, the tension term doesn't affect that value, that B parameter.
Well, they repel each other. The other thing to see, the elastic band, you see, it stretch and come back. They have a strong tension.
Yes, they have a string tension,
Yes, so it's a bit distorted. Tend to.
but they don't get as magnet.
Yes, correct.
Okay, so let's talk about superconductor in a bit more detail. So there is this sort of seminal paper from Patrick and Klein in 1969, where they argued that in principle at this transition, you kind of like have incredibly large conductivity. So even at the transition, you can't really like expel the flux, even if you were below the lower critical field for type 2 superconductor or below HC. So essentially they postulated that because the conducting timescales are so incredibly long, you start like stuck in this metastable state in the neutron star interior. And the details of the actual state that then arises is sort of dependent on characteristic length scales that you have. So the London penetration depth is on the order of like 100 Fermi, whereas the size of the core size of the flux tube is on the order of something like 10 Fermi. Okay, so some kind of like average magnetic induction value for that. Okay, so if I do that and assign every single flux tube a flux quantum, I can calculate that the number of vortices number of flux tubes that I need per centimeter is on the order of 10 to the 18. Okay, so remember for the vortices, I have like something like 10 to the 5, whereas I have something like 10 to the 18 per square centimeters for the flux tubes. Okay, so there's a lot more flux tubes per unit area than there is vortices. So you have essentially like one neutron vortex hitting a lot of proton flux tubes before you see another neutron vortex.
When you mention number of vortices,
Yeah.
you specify that they're neutron and proton vortices.
So yeah, so I usually say
their numbers are different, right?
yes. I mean, this is the flux tube, so those are the
That's proton
proton.
number, but when you had it, I don't remember, it was 10 to the 5 or
Then
6
it was 10 to the 5 for the neutron
Yeah.
vortices.
for the neutron.
Yeah.
Okay. So the protons is much lower.
Yeah.
By how much?
Well, so there's 13 orders of magnitude difference.
No, how many less proton vortices you have in comparison to neutrons?
More.
No, so I have 10 to the 18 proton flux tubes, and I have 10 to the 5 neutron vortices per unit area to get to typical rotations and magnetic
No,
zones.
but you also have proton vortices. So that's it.
Same thing.
Flux
This
cube
is
or
the-
vortex is two words.
Oh,
Those are the proton
Sorry,
vortices.
those are proton vortices.
Oh, okay.
Okay.
Sorry.
Okay, so you can calculate like the typical separation, and you find that's actually like on the order of 10 to the minus 10 centimeters. So that's actually getting close to the kind of like penetration depth, so the length scale over which the field falls off. So you get a lot closer to this value in that case. So if you like look at those two parameters, you can calculate what the typical Gibbs-Orlando parameter for that is, and you find as a function of these density parameters again, that's on the order of sort of like 3, which is sort of just above the critical value of 1 over the square root of 2. So in principle, if you like would just use standard Gibbs-Orlando expressions to derive the upper and lower critical field, you find those are on the order of sort of like 10 to the 14 and 10 to the 15 Gauss. Okay, so if you have a Newton star with a field of 10 to the 12 Gauss, you would in principle want to be here, so you want to have everything expelled. But because the time scale, as like when you essentially go this way in time, because it takes so incredibly long for these flux tubes to be expelled, you essentially end up in this sort of like metastable state where you have the field between HC1 and HC2. Okay, so how do we observe neutron stars? So in principle, if you want to like look at what the interior does and you want to constrain the physics, what you would have to do is find a way to actually access this interior using observations.
Can I stop you? It's a thing which I don't understand.
Yeah.
My ignorance. The number, I mean, the pairing gap of neutrons is larger than the one for the protons in the core. Is it correct?
Yeah.
We see it is not.
The pairing gap for the no. So the crustal pairing gap
In
is
the crust,
time
definitely.
that's larger, but
Yeah.
in the core, the pairing gap for the protons is larger than those for the 3p neutrons.
So would you say that basically the superfluid component in the core is mostly protons?
No,
No.
because protons are charged.
No, I know.
So
Yeah.
therefore, they can't have these superfluid vortices. So they only have this flux.
No, I understand, you see, but that's what I meant. Right?
Well, the thing is, there is a lot more neutrons than there is protons. So I have like a proton fraction that's on the order of
So
like
what happens to the
5%.
neutrons? Do they form vortices there too?
Yes, yeah. Although it's not entirely clear how that all works because
So-
they have to like go
yeah.
through the transition.
This is the thing you see which I don't understand. There are more neutrons than protons, but there are more proton flux tubes than neutrons. So what's the mechanism which leads to this? You see this balance, which is enormous.
Well, I think the imbalance just comes from the fact that you have
you see, it's
natural-
orders of magnitude.
yeah, so you have natural constants that tell you how much circulation you have within a vortex. So that's just given by a neutron vortex is given by kappa, and you have a flux quantum that's assigned to a proton vortex. Okay, so what's dictating you that massive difference is the magnetic fields you have overall in these objects compared to how fast they rotate. So you essentially have to recover something that you observe astrophysically, and that's something on the order of 10 to the 12 Gauss. Assume that the field is 10 to the 12 Gauss, and you have to create this by proton superconductor that is made up individually of flux tubes.
Field, it should be created by some charges moving, and you have very few of them. So that's the point.
Yes, but I mean, you still have like electrons that like swirl around. Like if you rotate the star, in principle, you can still have like a magnetic field created, right? So initially, you have like a lot of currents in the star before it's actually turning superconducting or superfluid. So you sort of like have this like field inherent to the star, and now you have to go through that transition. What do you do to that field? You break it up and you put it into
Can
flux
people
tubes.
calculate microscopically this density? Not phenomenologically. Can you see, knowing the density of the electrons in
Well, that would
core,
require you to
knowing
be
the
able to
protons
model
in-
10 to the 18 flux tubes. I don't think that's quite possible.
So you cannot calculate that
No.
number, it simply infers. So you need
Yeah.
that in order
Yeah.
to explain nature,
Yeah.
but you cannot calculate it.
No,
Is it
I
correct?
don't think so. Yeah, that's correct. Anyone
That's a
has
big
a
deal then.
different opinion on that? No.
That's a big deal, I think.
Yeah.
It's an elephant in the room and nobody has an idea.
I
where it
get
comes from.
to that sort of towards the end if I manage to get there.
The calculation is not different from where you try to estimate the vortex density in a superconducting sample. It's exactly the same reason. So you have
But that's not microphysics, right? I mean, that's not microphysics in some sense.
No,
Yeah, but
you see, you have to, you know the period of rotation of the star, you know the density of the charges, you have both protons and electrons. One of them creates a positive current, one is a negative current, because both of them go in the same direction. So now you have a net current, which creates a magnetic field. So how that happens? You see, having very little charge, you have to create an enormous magnetic field. How you do that? Can you do that? You see, not estimate from observation in order to fit the data, but can I calculate microscopically?
No one has a clue where the field comes
Yeah,
But I'm sorry,
I see the
this is not just that calculation, because the star is born with the collapse of a main sequence kind of star. It has a magnetic field, so there's an
Yeah, the magnetic field doesn't exist by itself. You need the current.
No, that's right, and it has currents. And
So
then,
where is the current?
wait. And then you go through the very complicated dynamics of the core collapse, at which point you will have charge currents and all things, magnetic field, flux conservation, all sorts of things going on, and then it settles down. And so in this period, you could have dynamo effects and all sorts of things active.
No, I understand, but is that understood or not?
This is not calculated, that's the problem.
That's not how.
No, and so it would involve some kind of simulation, but also it would involve much more than the simulations that people are able to do.
Okay, no, that's my question.
Because what you can do is sort of the millisecond collapse simulation with full nonlinear dynamics resolved to maybe 100 meters, which might not be enough. And then you need to track this for the shrinking of the proton neutron star down to a neutron star, which is say 100 seconds.
You see, if I have an electric field, you see from that I can determine what charges I have.
Yes.
See, I use pulse. I can do something similar. See, for the current, I know the magnetic fields. I can find out the currents.
But you don't.
So now, if I find the
you have no
currents,
information about any of these
No,
aspects.
that's right. But you can't. There's a gap. There's a gap, right? I mean, there are many potential internal magnetic fields that will give you an external dipole field of the kind of strength that we
If
see.
it's even a dipole, I mean.
No, but I'm just saying that will give us the dipole field that we think that we see, right? And it's just not. I mean, you're right. This is a massively important question.
Yeah. Okay. No, I simply want to understand.
You might be able to ask what's the minimal field, but then that's probably not stable, right?
No, but it looks
Then
to me
you
like
need to
it's
list
an
it
elephant in
in
the room
a-
is here, and we don't know about this, and go so quickly over.
I think it's just a massive, problem that no one has really
Let me just
solve.
add for context, so that it's clear how big this problem is.
No, that's the reason I was asking question. I want to understand.
I think it's a very important question. So just to add context, when people try to build neutron star magnetic fields in simulations, okay, the recent evidence is that not a single field that we're able to build as a sort of equilibrium type field is actually dynamically stable. We're not even able to build field configurations for neutron stars that would remain.
I understand.
And that's,
So you mean if you put electrons, protons there, and then rotating them, and whatever, we know equation of state and so on, they cannot do that.
It's a complete mess.
Interesting. Okay, thank you.
All right.
You also have this crust with these.
Do we have chalk? Can I draw two
No.
configurations?
No,
Currents
sorry.
may very well be. We don't really know where the current does. As Neil said, you can kind of invert, probably do MHD, you enclose the field, and then you work out the current.
Can you do that?
Oh, yeah.
As you don't quite know what the field looks like in the interior, there's many different currents.
I mean, if you want a dipole field, something like this, you can just have currents that do this. So you have hardly anything here, or you can just have a normal dipole that goes completely through the core. So you have a lot here. And you don't have currents that are mainly circulated here. So you really you could get from the exterior almost the same field, having completely different configurations in the interior, and no one knows what that would look like.
Is it possible that some of this magnetic field may be generated by something like INT?
Yeah. I mean, yeah, definitely. People have tried to do this, but they typically don't account for superconductivity. They just use normal matter. And again, that's not stable, as Niels just said. And it's not a simple like dipole field. They need like toroidal components and like lots of twisting up, and then I don't know how long they can live, have the configuration live, but it's really like
so
small.
they start with some magnetic field, and they do these simulations, so they decay away some characters.
Yeah.
So the reality is more like the picture on the right, you say. I mean, what you
I don't know.
No, we don't
No.
know. We don't know.
And if it's just this simple picture, these are very unstable. So just work it
No,
out.
but you see, you assume that most of the vortices are in the core. And
Well-
there in the core, I mean, magnetic fluxes, I'm
So
sorry.
I mean, if you want to, so first of all, if I like, if I get to that.
As you expelled it.
The number, so if, can we get back to that picture in a second? Let
Sure.
me just like continue a little bit, and then I can like go back to that.
Yeah.
Okay, so the way we can typically observe them is sort of like limited by what they kind of like the radiation that they produce. Okay, so neutron stars emit thermal radiation in the X-rays. So we can observe these from isolated objects and from typical accreting systems, where in the case of the isolated neutron star, as Niels said yesterday, there's sort of like indications that we might observe the supernova remnant in Cassiopeia A, which is something like 300 years old, to actually cool faster than we sort of like have predicted from the standard cooling models. And one suggestion to explain this is by having an additional onset of superfluidity inside the core, which gives you like sort of new ways to emit neutrinos, which is essentially the only way you can remove energy from the neutron star, and that leads to additional cooling. The problem is that these effects are really minuscule, and you need to be understanding your telescope incredibly well over a very long time scale of like several like decades. And we're currently like at that level where that real-time cooling is sort of like not significant enough compared to what we know about the telescope. So it's really hard to like actually extract information about the core in that form. Then Sanjay said this yesterday. There's other systems where I essentially have a neutron star in a binary, and the binary dumps matter onto the neutron star. You sort of like surpass the limit where this stuff blows up, essentially like a hydrogen bomb on the surface that deposits heat in the core. And because you sort of like either like stop accretion or you reduce accretion significantly, you can essentially observe the star cooling. So you see that thermal cooling as a function of time. And the timescales for that are sort of on the order of 10 to the 20 years. And it's much, much, much easier to observe these systems. And people have made a lot of progress in the last sort of 10, 15 years to understand how this quiescent light curve, so the decay of the temperature, is sort of related to the crustal physics. Now, to get to the core where a lot of these condensates sit, you need to understand the crust incredibly well. And they're only sort of just starting to get to the point where you can really like start actually probing the core. And that's sort of just like something that's been happening in the last 2 or 3 years. But it's really difficult to actually get out core physics from this, okay? So while this is in principle possible, and a lot of people do this, it's really not that straightforward to extract superfluid and superconducting parameters from this. Then another way we can observe neutron stars is by observing gravitational radiation that's emitted by these systems. They're incredibly compact, so if they rotate through space-time, they will disturb this fabric and send these like ripples out into the universe, and we can in principle detect those. So that was done for the first binary neutron star merger not so long ago. The thing is, for the waveform models that people typically use to actually extract these signals, no one really cares about condensates in some form or other. They essentially just use fluid balls. They have a specific equation of state. They sort of just at the stage where they introduce magnetic field and spin. So to like distinguish different levels of these waveforms where we can actually like extract parameters from the superfluid and superconductors, I think that's like not quite within reach yet, and will probably take a little bit more time. Although Niels mentioned that as well yesterday. In principle, you could like couple the orbit and the tidal effects sort of within the interior modes, and if you have these mode excitations, then it would matter whether you have a condensate in the interior or not. But again, that's sort of like not in the realm of what we can do right now. For isolated neutron stars, you have to create gravitational waves by sort of displacing matter within the star, so you need to create a non-vanishing mass particle moment. And one way to do that is essentially just like have either a mountain on the surface of the star, or you can actually like sort of like have oscillations in the interior. The signal that you get from these are much weaker, so several orders of magnitude weaker, but they are sort of like continuous, so you can integrate over a longer time. But again, that's sort of like not possible within the systems that we have right now. Although I'm looking forward. Well, I hope I'll still be alive and we see the first continuous gravitational waves from a neutron star. But it is really like not that easy, and it's not something that we can do right now. So the thing that we typically do to model or get any kind of information out of the star is using the radio emission. So neutron stars are very stable rotators. They have magnetic fields that are incredibly high, and those two axes are misaligned of the rotation and the magnetic field. So in this kind of cartoon, you have a rotation axis this way, you have a magnetic axis this way, and if you rotate, you essentially like have some kind of like cascade process here close to the poles that produce particles, and then subsequently produce that radio emission, although we don't understand how that really works either. But we do see those radio beams, so we can take advantage of this.
So that process where they are misaligned is not understood.
The process, well, again,
that's
that's
the mechanism, not process.
so it's super difficult to measure how large that misalignment axis is. We do think it's there because we see them as pulsars. So
I understand. Could be due to deformation.
Yeah, no, so that's that's the same picture, same problem, but what makes this happen? And if this evolves over time.
Else you see if it's deformation, then probably you can.
Well, so I think there's like ideas that if you, for example, make a supernova, make a neutron star in a supernova, and you have some kind of like axis symmetry, and you kick the neutron star in a specific direction, you might like be able to twist it in a specific form or other, which gives you preferred direction for the rotation axis. There is one way you sort of like can maybe like have them be misaligned by like 90 degrees with respect to something that's smaller. But in principle, you could also, by having them misaligned, can increase additional dissipation mechanisms that drive them to like alignment on large scales. There's really like a lot of open questions to what that axis is like. Yeah, so I think there's hardly any systems where we really have a good handle on how large that value is.
Are there models that say what that decay rate should be? That
There are.
And what are those time scales?
Okay, I would have to look this up instead of just giving. But so I think it's like not astronomical, but we're talking not about a human lifetime. It's probably more like close to the age of the system, like 10 to the 7 or 10 to the 5 years or something like that. So because they rotate and produce these radio beams, you can essentially see pulses. And neutron stars, because they circumambulate and rotate really stably, we can essentially like time them. So you just look at how often you see these pulses and you compare that to a template. And for about 2,500 systems, we actually have not only a period, but we also know how the period changes over time. So the period increases, so it sort of like slows down. And what people, or also astronomers, like to do is plot this in a so-called period derivative diagram. Okay, so you can
T is period in the formula.
Yes, this is.
Because usually period is T.
Not for pulsar astronomers. Yeah.
And I should warn you, Vanessa, this is actually the first PP dot diagram
I thought
that we've seen.
this might happen.
Unusual as that may be.
Okay, so let me like briefly explain what we see here. So there's like the black dots, that's the majority of them, which I denoted standard pulsars. They're sort of the pulses that are whose phenomenology is driven by their rotation. So essentially, the rotational losses that I get sort of driving the main characteristic features that we observe. And there is purple ones down here. They have relatively short periods, and we do think they typically produced by accreting matter from a companion. So a lot of these systems are binary systems. And essentially what we do think is that they're relatively old and recycled, so they've absorbed angular momentum from the accreted matter, which has spun them up, okay? So they sort of like characteristic different behavior to those that sit here. And then there's a system of a couple of objects very high up here that have relatively long periods. And if you look at this specific diagram, what I've drawn here are two sets essentially of parallel lines. So by assuming that these neutron stars lose energy, so the P dot is essentially driven by dipole radiation, you can draw or you can calculate very simply what the magnetic field that you would need to get a specific P and P dot value. Okay, so these lines are magnetic fields, lines of constant magnetic field. So this would be something like 10 to the 14 Gauss, which would mean that these very few blue dots up here are very strong magnetic field neutron stars, and that's why we typically call them magnetars. These other lines here are what we call characteristic ages. So you can essentially just like write down a very simple relation between the period and the period derivative and how that relates to the age. And you find that those systems up here are younger than those down here, which is sort of like consistent with that picture. The thing is, if someone gives you a Newton star magnetic field value or an age, typically where those numbers come from is from this diagram. Okay, so we can't really measure magnetic field strength. We can't really measure the ages unless we know where the supernova was that the star is associated with. So measuring magnetic fields is super difficult. And if we measure them, this number here in the normal dipole formula, is a constant value at the pole or the equator. This doesn't tell you anything about what's happening in the interior. Okay, so getting information about the interior field out of this is super hard.
I'm trying to understand that plot. If you can take that balance. You see, so the very slow rotating stars,
yes,
according to you, they are very young.
Yes, and have high magnetic fields.
But if they slow down, then the period increases, right? So they become older and older. But that's counterintuitive with this plot.
Why?
Why? No, the period is longer.
So the thing is, like, it's
the period,
really
you
not
see, you
that,
go to the right.
Yeah, but so like going to the right, you don't see anything going on here.
You go to the right.
You don't see anything going on here. So this is like a snapshot in time.
No, I understand that, but if you think of the stars, what happens? You see, 100 years ago it was in the black region, but now it's in the blue region.
No, sorry, that's not the same thing. So what you might observe is like two characteristic different like populations of neutron stars, which they are born. Okay, so these objects might just be born very with very high magnetic fields, whereas those neutron stars might be born with different magnetic fields.
So this is at the inception sometimes.
Yeah. So like Vela and like Crab, they sit somewhere up here.
So
okay?
you don't have an evolution, is it from there?
No, they don't move up this way. No. It's like, well,
to be
let's
fair,
let's
that's predictable.
Right.
let's
So the simple
not
picture is
That's not debatable what happens, because one of the big questions is how does the magnetic field evolve? And so the story that is kind of the most plausible, maybe of the ones that are out there, is that the points will evolve almost straight down in this diagram.
or do something like
Yeah, they will. There's some shape to that which might explain why. If you look at the blue dots only, they almost stop at the.
I can do that.
So why there are none slower than that?
So either it's because of selection effects, so we wouldn't see them, or
No,
they evolve straight down.
No, but the fact that you don't see them, it explains why there are so few blue dots.
Well, they don't. Yeah, they don't last.
Well, so
you
the thing is, like,
you see the black ones because it's easier
I should
to
say
see.
one.
Yeah.
Can I just say one more thing? You don't observe these as radio pulsars typically, so you can't observe their rotation. You can't observe their properties
It's like
using
detecting
radios.
efficiency.
So you need like an X-ray telescope to do that, and that's way more difficult.
Okay.
So I think there's like 2 more dots down here actually now, but I haven't made this diagram in a while.
Okay, thank you.
Okay. Well, we're at the 50-minute mark. Can I talk about what I wanted to talk about now?
You have to teach us first.
Yeah, no, that's good. I think that's the whole point of this, right?
The morning
But-
is yours.
Are people still? I mean, I hope you're still going to stay around a little bit. But I might like.
we can have a break.
We can have a break if you're.
No, I'm not tired. I'm just like I don't want to bore people.
If you've had enough of us, you can take a break.
Yeah.
Okay. Well, no one's sleeping. Okay, so most of what we like know about the quantum condensators inside the star is essentially due to what people have done studying lab systems. Okay, so we've sort of like tapped onto a lot of like the developments that were originally made and essentially like sort of rewrote the equations in the way that apply to the neutron star. So what's been sort of clear from what we've talked about so far is that we need better macroscopic models that account for improved microphysics or mesoscopic physics. And when I say that I want to test some of these in a laboratory system, I am not telling you that we can rebuild an entire neutron star in a laboratory setup, but what I want to do is like look at specific systems that I can use to study various neutron star physics aspects that I think are going to be important. Okay, so I'm kind of like picking out specific things in the neutron star case that I think might be important, and I want to try and study that mechanism better using a laboratory system. And then I want to put that feedback back into like how I write down a hydro model for the neutron star. Okay, so the classic setup where we think superfluidity plays a role is glitches. So I think several people have heard about this last week, and Tina has also briefly mentioned that. So in principle, the star spins down because it loses energy like an electromagnetic dipole. So you should, in principle, on a very like simplified sketch, where you look at the component that you observe, which is the cross, because that's where the field is definitely anchored in some form, and it's going to like slowly decrease over time. Okay. So typically, what you don't expect is this thing to suddenly speed up, so to get faster. But that's actually what is happening. So that was sort of observed really shortly after the first neutron star was actually observed in 1969, I think it was a year later. So the Vela and the Crab pulsar were both observed to have these sudden, what's called spin-up glitches. Okay, so the time scales for those, for this, is relatively short. It's on the order of like maybe a minute or two maximum. And the idea that you have is, well, you can spin up the observed component by having another internal component that's somehow rotating faster. So it's decoupled from the actual component that you see spinning down. And then something happens, they recouple, and you have angular momentum transfer from that faster rotating component to the crust. Okay? So one way this could be achieved, and it's sort of like an analogy to what you observe in proton vortices in lab systems, was first proposed by Anderson and Ito in 1975, that you can actually have this internal component decoupled by assuming that it's a superfluid that's pinned to the vortices in the crust, for example. Okay, so you have some kind of component that's decoupled, that's the pinned superfluid. As the star spins down, you increase the lag between those two, and then something happens at some point that recouples them, and sort of like have this like recoupling process, and then some like really long-term recovery. Okay, so this is kind of the picture that I had in mind earlier. So I unpin my vortices, and then they're free, and then they experience coupling on small scales, and I can probably assign that some kind of B value. So when in these like hydrodynamical models that we typically use, this kind of recoupling and the recovery are essentially characterized by these mixture friction coefficients B. Okay, and then directly related to the mesoscopic physics.
Just to clarify, the vortex velocities you mentioned earlier, that was sort of in the range 10 to the 2 to 10 to the 6 centimeters per second. That's when they are in the post unpinning. In that
would be like right here. Yeah. So, but the number that I gave you is a microscopic number. This lag here is a macroscopic average between the two components. They're not really related. So you can have like very different microscopic relative velocities compared to that lag. Okay, so the evolution of the observed component is typically modeled within these body averaged multi-component frameworks. And the first thing that people sort of did when this all came up was to actually like extract these long exponential relaxation timescales from observations and compare them to microphysics in the crust, and for example, explain this in terms of specific crustal pinning energies and the temperature that you get in the crust. This was all sort of pioneered by Ali Alper, and he's worked a lot of this on this since then. But that was sort of like focused on the long-term timescales, because that essentially was all the information that people had So typically when you do this timing, it's not like you track this whole thing really. And what you do is you might have a point here, you might have a point here, and you maybe have a point here and here. So because this is like shifted up, you can kind of tell where something has happened. And you can like track these like exponential relaxation timescales on the order of like months, weeks to several months, much easier. But recently, Paul Freeman et al. Managed to sort of catch a glitch in the Vela pulsar, which is one of the ones we study a lot, for the first time in the act. So they observed the Vela 2016 glitch essentially by pointing the telescope on Tasmania onto this neutron star exclusively and just let it stare at this. And they managed to sort of like track this behavior of the neutron star on very short timescales. And we sort of like provided a very simple data comparison with our theoretical models that was sort of based on like realistic crustal microphysics to actually learn a bit more about the coupling processes in the core. The problem is, this is kind of the first observation in this room, and the data is still super noisy. I mean, you obviously have like issues with like using your telescope, and there's like a lot of noise in the signal itself. And the thing is that Vela only glitches every 3 years, okay? You don't know exactly when this happens, so no one's going to like use the big radio telescopes to stare at a specific object for 3 years the whole time, okay? So the Tasmanian group actually wanted to like do this for the next glitch again. It was supposed to happen this year in December. Unfortunately, neutron stars are not that regular, so it decided to glitch last month, and no one was looking. Okay, so to actually do this like with a systematic analysis, this is just, I mean, you can try this and it's like nice if it fits, but to like do that model comparison properly, it's just really difficult. So there's actually, that's the only kind of like lab experiment that was ever focused on like really testing neutron star physics in some sense, was performed in the 1970s and 80s by two Georgian physicists, Zakatse and Zakatse, and they essentially like tried to like figure out if these long relaxation timescales after the glitch can be associated with a superfluid component. So they built something really simple. Well, it was like 50 years ago. So they had this like kind of cryostat, they had a helium bath, they had a vessel that they could dip in, move back up, spin it up, and then let it evolve freely. And there's like a tiny mirror somewhere, I think here, they used to just shine a light on, and they used to like record how fast this rotates, okay? So they essentially like did these kind of spin up and spin down simulations, experiments in a very like systematic way, by looking at various temperatures, vessel configurations, and rotational properties. And sort of like the only time that experimentalists really like built a dedicated experiment to study astrophysics or motivated by astrophysics. So the problem is that this is the only kind of like data set that people have, and astrophysicists have tried to like actually use that data and compare their models to it and sort of like extrapolate that knowledge to the neutron star. The problem is that the data is super, well, it's pretty bad. Let me show you how this data looks like. This is how the data looks like. So the people have tried to like do these kind of comparisons are essentially like looking at where the middle points of these points are, and they extrapolating what this would correspond to. There's also a lot of uncertainties with like the geometric setup that they use, because sometimes they give the radius of the sphere for the same kind of like plot, and then the next paper is the diameter. So there's really like not exactly clear what their exact setup was. And I don't think really anyone has access to the original data anymore. Yeah.
This is from, I think it's 40 years ago. People are using the data, and the data is not on the level that people would like to have. Why doesn't any experimental group actually try to redo that with our?
No one cares.
Which group is
Which payoff? Always is the payoff. At least.
Why would you? Yeah.
They all have relevance to neutron stars, but they are going to be funded by the helium community. So the question is, are they interested in that?
But no one has space.
Yeah.
So the thing is, you might not even necessarily. They did this also with cylindrical.
Research is very structured. You work in this direction, that direction, this direction, this is across field, very far away. But So
Yeah,
that's.
I'm just because if people are actually using that, this means that this field is interested in these kind of experiments, which is already some kind of payoff in some sense.
Oh yeah, no, there's no doubt that if someone were to invest in building a kit that had the spherical geometry, because I think that's important, right? To redo or actually do these experiments in a modern setting, that would be something that would be enormously interesting for any people who are working on neutron stars in general. That's clear. But that point, it's not as if that point has not been made.
So maybe one of the cool things that they actually, and they weren't looking for this, is that they actually observed a laboratory glitch in the system. Okay, so they sort of like just let their system like naturally like spin down, and then they recorded the data and they saw something like spin up. Okay, so this is tracking the rotation period of the vessel.
I think the neutron star physics astrophysics should fund these experiments. That will work.
The thing is like this.
Funding for them.
Out of your own pocket.
The credibility we would have for fighting the case.
I think that's the main problem, because if you write this to like astrophysics, it needs a lot more money than what we typically like our grants are, just because you usually have people power and computer power, right? So you have to like find it.
How important is that?
I'm not exactly that sure. I think there are experimental groups that would be very happy to do this, right? But they are not. So just like we are not able to explain how they would do the experiments, they cannot explain the justification for doing it. So there has to be a cross field, as you say, and that dialogue is complicated.
And it's only like we're trying, but I guess it takes some time to get to that point, right? We use different language to just like describe the same thing sometimes. So to just get to the point where you can actually like, say, well, I want you to do exactly this experiment because that's the benefit I have. To get to that point, I think that's going to take a little bit longer.
But there are workshops also for experiments in theory. I feel like experiments from that direction with.
I've talked to quite a few, but like they always seem very keen, but then. Interest is there, but to get that one step further is, I think there's just a little bit of like, I don't know.
And
pushing.
writing kind of a grant, like cross-beam grant, which sounds always very nice.
But I mean, that would be a lot of effort, I think. And well, it's something that I would like to do at some point, because I mean, that's why I'm doing this. I think there's a lot of like overlap and interest.
So the difference T1, T2, it's only a few seconds, right?
Yeah.
So it's clear that that was intrinsic to what they measured, or there was somebody passing by.
I don't know that. So I'm like,
doing this.
I said before, maybe you can.
Probably Georgia.
I honestly don't know.
The Soviet Union. That triggered that. So why did it happen?
Never heard that suggested, but that's a very interesting.
But so I know Jim Soule has been to that lab, and they did it on like I think a massive oil bath. So it's like super basic. I mean, it's like 1970s Soviet Union physics. So it's like really not.
Maybe
that
they had a
straightforward.
party. They had a big.
I don't know, but I mean,
dancing that caused it.
You would like to like maybe try and see if that's real or not. I think from like so you have to repeat it, and I mean, you have to start somewhere. So I think
and 10
this
to the 13 is simply the magnitude of the change there, which
so
is required for the.
Sorry, this is for the Newton star case. So
this for Newton star.
So this is like this
okay.
height for the Newton star essentially. And
out of 10 to the 18, right?
No. So remember, 10 to the 18 was the proton vortices. So I essentially have 10 to the 5 Newton vortices per unit area. So I have to involve basically almost the entire inner crust, or large fraction of the inner crust.
So you have to do that.
Yeah.
Okay.
So this is definitely going to be a lot less vortices. I mean, a helium setup has like, I don't know, 1,000, 2,000, maybe 10,000 vortices. So, but that was something that you can actually like study like systematically. How many vortices do you really need to actually like kick off a glitch like this? Do you really need 1,000? Because if it's like maybe only 100, maybe you can do it in a BC somehow. I don't know. But yeah, so like what happens here is super unclear. So the trigger that actually kicks all this off is really not certain what's going on. So this kind of like systematic analysis that you can do with this would be really useful, I think, to study in a laboratory setup. Yes.
Exactly on this point, is it possible, for example, that it's not really an unpinning that actually happens? vortices are still being where they are, what actually might happen is there is a catastrophic event in the inner. So the vortex is basically pinned, and then because of a complicated process with them, it reconnects. So the leftover actually repins on the crust, but now it's a very, very small particle. And the majority of the vortex inside it now transits into a different counter state, which actually makes you rotate.
Well, so you have to spin faster. So you have to like get, so this is a spin up. So you spin it down and you have to like rotate, you spin up the crust. So you can, yes, you have to spin down the superfluid. And how you do that, I think, is not, well, so within the central picture, we just say, well, they unpin somehow and move radially outwards. And you spin down the superfluid that way. And on a large scale, you transfer angular momentum to the crust and you spin it up. But I'm pretty sure that you can come up with another kind of like way to rearrange your vortices in the interior somehow to actually like make this happen. So how this actually happens, I mean, again, we just have a simple picture. It's not 100% clear that's what's going on. Yeah.
So if they did this experiment 40 years ago, and then it basically turned out smoothly apart from one glitch, is there a danger that if you redid the experiment in much more controlled conditions nowadays, you wouldn't get any glitches?
I don't know. I mean, again, maybe this is something you can only do in 17.
Also, because I think you just chopped it down yourself. No, not here.
I don't know. The thing is, if you, I would assume if the Newton star in the glitch is somehow related to the vortices, then you have to have this kind of physics, because it's like, I mean, it's just a simple picture. You have to have this in a laboratory setup as well. If you don't see it, you might have to like ask yourself, well, why don't you see it in the lab system, and why the hell can you get this in a Newton star?
But there might be complications, like you might have to make sure the sphere has pinning sites on it.
Yeah, so they actually did. So they did this in the experiment by gluing plexiglass crystal onto the inside of the sphere. So they created like points where the
and helium was inside.
Yeah, yeah. So they just like they stuck. Sorry, they stuck like plexiglass crystals on the inside of the sphere to like create more points where vortices could create.
What's the bottom?
This is like the helium bath, so they moved this down, filled it up, moved it back up.
Oh, it fills up from the bottom? Yeah, okay.
Maybe it fills up, it would not be filled up from the top, right? It was completely filled up.
Okay.
But yeah, then I'm not an experimentalist. I mean, I don't.
I can tell you that perhaps one reason
no, I think that's probably true. Also, I mean, this has been done like 50 years ago. Why would I do it again? But for like from our motivation point of view, there's a lot of benefit for me having like another data set that I could compare my models to.
Yeah, it's just that in the helium community there are driving forces that
yeah, no, I understand. Yeah.
So does this seem like a reasonable thing to do?
They have their own problems.
I'm not aware of any person who's actually thinking of doing something like that, because I know lots of research and experimental groups, none of them actually. In fact, in helium 3, most of the research nowadays has to do with the flow past of.
But Wade has his droplets of helium. They can spin up, right? Wade, well, in Florida.
But so they have like no bound.
No, what's the thing in Florida? It's California.
No,
they can put in this.
No, the droplets of helium, it's not in Florida. It's Villisov in University of Southern California.
Wade,
right?
We're talking Wade.
Wade.
Yeah, but he talked about that experiment on Villisov.
But he said that they can do that.
Wade is levitating helium.
At that time,
he is.
But
he said that they can get like the helium to form some outer layer. So I don't know.
Oh, so you like have helium on helium?
The not helium, the hydrogen rather. Sorry.
Oh,
So
okay.
the
Can I
these
suggest?
particles-
Yeah, sorry.
It's like, I thought we could maybe in the discussion group today, like later today, actually like talk about like some of these aspects that I mean I don't know.
You might finish giving a talk, right?
No. But
No, you
by
don't.
the
Oh, okay.
suggestions of other things that we could do, maybe we can like talk about this
Yeah,
afternoon.
Yes.
Okay.
Okay, so you're leading the discussion session.
I can do that. I mean,
Okay.
that's fine.
Thank
I'll
you.
stand at the door. Okay. So another thing, and Neil sort of alluded to that as well yesterday, is that one thing that's really important for the Newton star is that we have this very distinct interfaces. Okay, so these are the gaps again, and this is the that it sort of corresponds to. If I draw these gaps, and I assume that I kind of like have this as the cross-core interface, then there's some like overlap between the 1s0 gap and the 3p2 gap. Okay, so it's never really been looked at what happens at that interface, because we do think that the gaps overlap at some point. So what is actually like happening is how do I go just from here to here? Is that what I'm doing? And what do the vertices do there? Okay,
So
that's one thing.
Would that mean that if you reduce the overlap, there will be no glitches, for example? Could be the glitches you see exist because of that overlap, because otherwise you see you'll have independent system rotating how they want.
Can I show you another plot like that in a second, or like talk about something else like that in a second? There's another transition where we think that, well, in principle, we do have this type 2 superconductor somewhere here, but you can actually write down that at higher densities, so somewhere here, you actually like you drop that Ginzburg-Lambda parameter below that critical value, so you actually should have an intermediate type 1 state. Okay, so what happens in the superconductor from here to here is also not clear. And then again, well, we don't really know if these gaps like close, if they actually sharp, and if so, what happens like left or right of these. Same thing here or here. So it's really not that clear what happens at these transitions that we have in these Newton stars. So one system that we could maybe use to like learn more about the interfaces is use Helium II, Helium 3, which becomes superconducting superfluid at something like 3 millikelvins, and is also undergoing transitions by Cooper pairing, so it's a Fermionic system. And because of this sort of like internal structure of the Cooper pairs, there's actually very distinct superfluid phases as a function of magnetic field, temperature, and pressure. So there's the B phase, which is sort of very similar to Helium 2 or the crostal neutrons, and there is the A phase, which has very anisotropic behavior and is essentially similar to the core neutron superfluid. So vortex behavior across these interfaces can or has been studied in a laboratory system by looking at 2-phase samples of helium. So in this kind of like vortex line simulation, this is the A phase and this is the B phase. So what essentially is different is that those two have different mutual friction coefficients. So the strength of the friction processes in both are different. And Neil sort of said this earlier, we do know, I mean, I showed you these graphs earlier, the Newton star definitely has different mutual friction in the cross and the core. So we sort of have a setup where this is definitely also going to be the case. What we don't know is what the ordering actually is. So in the A phase, the coupling is stronger than in the B phase. In the Newton star, it's not quite clear where this actually switches, because I showed you earlier, we have these like different curves, and it's not quite clear which is the dominant one. So in this kind of like simulation that they did, and they actually performed NMR measurements with it, this is just sort of more illustrative what's going on. So at this interface between those two, the first thing that you see is because this A phase spins down faster, essentially the vortices move out and they like pull on the ends of the B phase vortices. So they bend radially outwards and build this vortex sheet. And because they have this additional pull on them on the interface, what happens is that the B phase builds this tangle. Okay, so you have increased dissipation in the B phase because of the presence of this interface. So in the absence of this A phase, the B phase spin down is just laminar. So you essentially increase the spin down rate by having this interface present and having it touch to the second phase. And another thing that you see here, and that's also sort of applicable in the Newton star case, you look at it from the top, you see sort of the cross section of where vortices are present. So there's basically no vortices in the center anymore. They're sort of like concentrated closer to the container bucket. So in principle, if you were to like use the kind of hydro model that we do, we assume that there's a continuous distribution of vortices across this. This is no longer the case here, so you actually have differential rotation. If you take fluid element here and be non-rotating, it will be rotating somewhere here, okay? That's super different to any kind of like setup we've ever looked at in the Newton star case. And if that really happens in some form, that should definitely change the physics. This interface, additionally, if you like make that have the relative friction satisfy specific parameters, can actually become on top of that unstable. So you can excite like Kelvin-Helmholtz instability for long end, and you can actually sort of like transfer circulation like blob-wise, essentially, so that you disconnect an element of the vortex and move it into the other system. You can actually like have like transfer of circulation that way. And the only kind of like Newton's star astrophysics application that this whole system has ever seen is by Alpha Mastrano and Malatas. I don't think we talked about that last week, right? Yeah. Where they suggested that actually by like having this like transition of circulation across the interface, you can actually remove vortices and unpin them. So they suggested that would be a way to trigger the glitch. So you have two fluids, and you can essentially have relative velocities on each side.
Okay.
So by doing that, you start bending the interface.
So
it
you
doesn't.
don't have a straight one.
You start like bending it, and then you like bend it so much that you like move some of the bottom fluid.
This
into
is
the
like
top one.
snaking stuff like
Snake. Yes.
Snake.
Okay.
Hmm? Yeah.
Okay. I assume you're talking about pasta. Yeah. Okay. Has anyone mentioned nuclear pasta like last week?
We mentioned in passing.
Okay. So another thing that, let me just go back to this, is that the majority of the mass in the crust here sits actually really close to this crust-core interface. And typically, the picture that we have in mind when we look at what's going on is that sort of like in the outer crust, you have this like very standard BCC lattice, but as you go to higher densities, you start deforming these individual structures. So you turn them into like, from like perfect spheres, you can turn them into gnocchi, or you can like start making like elongated spaghetti, or you have lasagna shapes, hence they refer to as pasta. So the majority of the mass that actually sits in the crust is located in this pasta region. And the picture is way more complicated than this here. So these are molecular dynamics models of different slices. So this is sort of like a pasta kind of layer. This is sort of more of a disordered gnocchi face. And so this is at lower densities, so this is at higher densities. And you sort of see that this is very different to the kind of like simple picture where I just have a nucleus that's sort of permeated by a Newton superfluid. So I think no one has ever really looked at what this kind of like structure actually does with respect to the superfluid and how vortices could interact with that. I assume you can't move vortex this way. You might be able to sort of like have it sit somewhere in between those, but it's really not at all clear how this kind of structure interacts with the superfluid. And in principle, that's kind of the parameter that we would use to actually model glitches properly, I think. So I think there's sort of like a really like big picture for crustal superfluid physics.
Might have very short vortices.
Yeah, so you could do that probably, but then you would, I mean, so the parameter on microscopic scale that I want is this B. So how would you calculate that B? I have no idea. So there might be like a way to study superfluid properties and vortex dynamics in the presence of impurities by looking at what Helium II does in silica aerogel. So it's sort of like this very porous structure where if you have just a few percent of like space that's free, you can actually create superfluid phase of helium in it, and you can sort of like people start to study what's actually going on with the superfluid in there. But that's the closest thing I can think of that comes to like studying this in a laboratory setup that's close to the pasta phase. We've heard a lot of ultra-cold gases. Well, I think the main thing is that you have a lot of possibilities. And the main thing that we should be a bit careful about is, well, we have, I mean, this is a typical snapshot. We have like maybe like several hundred vortices. we have a lot more in the Newton star case. So while you can definitely study like individual vortex physics, it's not that clear how you can just generalize this and scale this up to like larger scales. What it would probably be very useful for, and we also talked about this yesterday, is that you can definitely like find a way to study interactions of individual vortices with defects like you, for example, have in the Newton star crust. And maybe you can even make something that's non-spherically shaped. I have no idea. Or you can, we talked about this as well, study like the interactions of different types of vortices, and you can probably start from like a more theoretical point of view before you actually try and set this up somehow. There, everyone always tells me everything is possible. Well, I want to like understand what's actually feasible to do. So, what are the really like limitations that you can get? For example, how many vortices can you actually create, and is there a way you can maybe like even have a two-component BEC and make like glitch happen somehow and like have stuff pin? Well, I don't know enough about that.
The main difference is not the number of vortices. The main difference is the density. Line density is much higher than in neutron stars. See, the separation between them is
well, I guess
coherent.
I would, if I would want to, well,
which is not truly neutron.
Yeah, that's true. But let's say I use a two-component system and I use a second component that only has one vortex.
Yeah.
Can you do that? I mean, I
Yeah,
you can do that, right? So you could
Yeah.
like try and like see if you have one compared to a lot of others.
People can create only one vortex, creating two, and so on.
Yeah. So I mean,
It can be done.
And then people have done experiments where they're pinning on optical lattices.
yeah. Oh yeah. So yeah, I did actually say that. Yeah. Or you can like move optical lattices through each other and study like that kind of physics. So I think there's a lot of options. Right now I wouldn't have like the experiment that I would want someone to do. I think that would require a bit more thinking. I'll skip that. Okay, so the last thing that's sort of related to this picture again is that every time we talk about macroscopic superconductivity is that we talk about this kind of phenomenon as like a snapshot in time. So we look at like something that's completely in time independent considerations, and we never really like think of it from the point of view is what actually happens as a function of time when the Newton star cools through that transition. Okay, so from the gaps we probably know that the neutrons are still normal when the superconductor forms, but how it forms and like what kind of structures you form in the presence of these other components is really not clear. And the kind of like very naive picture that we have with like individual vortices regularly distributed is definitely like not, well, I don't believe that's to be correct, maybe on some length scale. But in laboratory systems, you have all these like very diverse flux distributions and very like domain-like behaviors. Sometimes observed if the Ginzburg-Lande parameter is close to that critical value, sort of the case here, and we are quite close to that value in the Newton star case as well. And then there's another kind of like system where these like very irregular distributions of flux have been observed, and that's in MGB2, which is a two-gap superconductor. So because you have like different ordering of the respective length scales in the system, you can actually like have different repulsive attractive interactions that sort of lead again to this like formation of domain-like structures, and that's typically referred to as 1.5 superconductivity. So is there something like this also present in the Newton star where I do actually like have kind of like two condensates that have specific gaps? Toby might be talking a bit more about that tomorrow. Okay. Well, that was the longest over I've ever gone. Okay, just a quick conclusion. So it's really difficult to probe the physics in a Newton star, specifically in the interior, using observations, but we sort of need these better macroscopic models. We do think there's at least these three condensates that didn't even go into the core, where you could have like color flavor locked superconductors maybe, or other superconducting phases. And the majority of what we know today comes actually, or is motivated by these laboratory systems, okay? So I think there have been a lot of advances in understanding these lab systems. And while this whole field of like studying Newton star quantum condensates sort of kicked off as like a very massive, like, well, it was a very interdisciplinary field that's kind of died out in the last couple of decades. So I think there's a lot of ways we can actually like talk about this in a little bit more detail and try and find like ways where we can sort of benefit from from each other. I'm not saying that someone will build me a lab system, but maybe there's some stuff that people have already done that I can just like use and actually understand something. I think that would probably be the most ideal scenario. Okay, thank you.
So does anyone have any questions? If there's nothing pressing, we'll resume discussion this afternoon. Yeah, that's fine.
Yeah, maybe people can think of like what they would like to do. I mean, I've like talked about a lot of different like elements of the star now that we think might be important, but we don't really have a clue. So maybe you can come up with something until like in the next 3.5 hours, like you. But even if it's crazy, I like to hear crazy ideas.
I'll send a message out. Maybe we can get some of the experimentalists to come back and join the discussion.
Okay.
All right. Thank you very much.